Give acids and bases, and we'll take it to the next level and really look at what Ka and what equilibrium is and the different definitions of acids and bases and what pH actually means. So the first kind of idea of acids and bases was developed by Arrhenius. This is what I call the Chem 1 definition of acid-base theory. Okay, it was the simplest of all. So this is why I call it the Chem 1 definition of acid-base theory. It's because anything that has like an H in front of it, like hydrochloric acid, nitric acid, which is HNO3, hydroiodic, that type of thing, all start with an H. Okay? Boom, there you go. So it has an H in front of it, it's an acid. Cool. Bases have no H on the end of it. Sodium hydroxide, potassium hydroxide, strontium hydroxide. Okay? And it's a very, very good, basic, simple definition. But it has limitations. Limitations are that it only works in aqueous solution. Okay? And that covers a lot. Okay? So don't think, wow, that's just so old school. Okay? This covers a lot of the acid-base theory that took place. Okay? And you all have done titrations. You've taken hydrochloric acid and sodium hydroxide, and you've done this, and you've done this neutralization, and you get water and NaCl. You are literally producing salt water. Okay? So out of this neutralization of an acid and a base, you get water and a salt. Okay? Boom. You want to make some salt? You're at lunch. You're out of salt. Bummer. Go grab some hydrochloric acid and sodium hydroxide. Neutralize it. Evaporate the water off. Boom. There's your salt. Okay? Literally, you are going to make sodium chloride. Okay? You are going to make salt water. Okay? And that worked for a long time. But what they observed was that you had situations where there was acid-base reactions taking place, but you did not fit them. Now, the next one, and this is going to be important in terms of timing, it's what's called the Bronsted-Lowry theory. Okay. And the important part of this is the timing. This was developed in 1923. So acids are proton donors, and bases are proton acceptors. Okay? Now, this wasn't developed literally about 102 years ago. Okay, this definition came into being. Why do you think this wasn't developed like in the 1800s? Sure, we didn't know anything about protons. Okay, this theory could not be developed until we knew that there were subatomic particles that we call electrons and protons. Okay, that's why this could not be done until 1923. You look at chemistry books prior to 1920, and you try and find the words electron, proton, neutron, they weren't there. We hadn't found them yet. So this is why this is a relatively new idea. Now, the other thing that comes out of this, not only do you have acids and bases, you also have conjugate acids, space here, conjugate acids, and conjugate bases. So let me give you like a great example of this. Okay? So we're going to take hydrochloric acid, HCl, and we're going to put that in water. Okay? So this is the limitation of the Arrhenius definition. Okay? The Arrhenius definition won't work for this interaction that we're about to look at. You have the acid, you have that classic definition of the acid, you have hydrochloric acid, cool, okay? But you have water. Now, you can think of water as being H and OH, okay? But that really doesn't fit like the true definition of a base is defined by Arrhenius, okay? Because that had to be like lithium hydroxide or sodium hydroxide, okay? Now, And this is going to form the whole basis of what we're going to talk about today. And we've talked about this and we've talked about this. So here's what's going to happen. Visual. Here's hydrochloric acid. There is a bond that exists between these two particles. You have a negatively charged chlorine and you have a positively charged hydronium ion, otherwise known as a proton. Okay, literally, this is just a proton. It's H plus. It's a proton. Okay? We make it sound fancy like, oh, H plus. It's a proton. That's all it is. It had one in Chihuahua and it gave it to the chlorine. But there's a bond that existed because they have a shared Chihuahua. They gave that Chihuahua over there. And they're positively and negatively charged. So you have this bond. They're together. Here's HCl. Here's the water. Now, to understand what happens with strong acids, weak acids, conjugate bases, you have to understand this boils down to a tug of war. If you understand the tug of war, you understand what's going to happen. So here's your HCl. Here's the water. Oxygen in, positive or negatively charged? Negative. Has excess chihuahuas. This is negatively charged. This has a deficiency of chihuahuas. Here's the hydrogen in, that's positively charged. So along comes the HCl. It has a decision to make. Do we stick together or do we split up and hook up with the water molecule? That's the decision that it has to make. So the hydrochloric acid basically says, hey, love you to death, but I'm out. Okay? You showed up as prom and you are friends. And now you're splitting up once you get to prom. Because there's other more attractive people to go hang out with. Sounds cool, but that's the reality of it. So the oxygen end of the water molecule takes in the proton, because that's negatively charged. The chlorine end comes up down here, because this is negatively charged, because it has excess Chihuahua. It's going to come down here and it's going to hook up with this. So out of this, what we get is that we get hydronium ions and basically chloride ion. Okay, so the chloride ion is going to be floating around. They're technically attached to the proton, we write them as a separate thing. So here's the deal. When it's a strong acid, and hydrochloric acid is like the poster child for being a strong acid, what happens is that once this takes place, all of this shifts over here. Okay? None of this, or very, 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 very tiny amount of it exists in this form. This is the vast majority of what's going to happen. So this is where you have a situation where the Arrhenius definition fails you, where the Bronsted-Lowry definition works. So in this situation, the hydrochloric acid is a Bronsted-Lowry acid, mainly because of the fact that it gives up the proton. Now, here's the weird thing with water. Water is going to be a Bronsted-Lowry base. And you think, well, that's weird. It doesn't have hydroxide on it. It doesn't. But what's going to happen is that the water is going to take in that proton. That's what makes it a base. So this is going to get shifted over here. Now, out of this, on the other side, if you have an acid base, you also generate a conjugate acid and a conjugate base. So to figure that out, over here, to figure out which one is the conjugate acid and which one is the conjugate base. And you always have to have that, because if you have an acid-base reaction, you have to form two products over there. So I can't have an acid-base reaction without forming a conjugate acid and a conjugate base. So over here, this is going to be my conjugate acid. Now here's the easiest way to figure out which the conjugate acid is. Because if you were to take the hydronium ion, this, and have it go back to being water, this would have to give up that proton and separate this back out. So if you wanted this to act as an acid, you would have to take away a proton. And by definition, that's what a Bronsted-Lowry acid is. It gives up a proton. So my hydronium ion is my conjugate acid. My chloride ion is my conjugate base, because it would have to take in the proton to go back to being HCl. So whenever you have a Bronsted-Lowry acid-base reaction, you always form a conjugate acid and you form a conjugate base. Now, there's a couple of things that are important. Just like before, the sum of all the charges on both sides have to be the same. I have no charge on the left side because everything's neutral. I do have charged particles over here, but if I take the positive one and the negative one, that still adds up to equal to 0. Cool, great. This one's relatively simple. But this is a situation where you had an acid-base reaction taking place, but it didn't fit the Arrhenius definition. That's why they had to come up with something new. Okay, a little bit more complicated. So now we're going to take ammonia, which has a very, very strong punch order. I'll do this demo later on. I don't have time today, but we'll do this demo. Ammonia is it's like, if you ever smelled like cleaning products that have ammonia in it, they have a very, very strong odor, okay? That's what that comes from. So we're going to put this in water. And out of this, we're going to get and hydroxides. Okay? So, here's the story. In this situation, you have ammonia. You have one nitrogen surrounded by 3 hydrogens. Put it in the presence of a water molecule. If you look at this structure, that's a nitrogen, a hydrogen, and up here you have one unbound pair of electrons. So the top of the ammonia is negatively charged because it has an unbound pair of electrons. And you put it in the presence of the water. Okay? So here's the water, goes the ammonia. So let me give you this picture because that's going to help. Hold on, give you one second. By the way, you ever become a chemistry teacher? I said it. Okay, so here's the ammonia, NH3. Negative end up here. You got this division because there's one unbound pair of electrons because nitrogen has 5 valence electrons. 3 of those electrons are tied up here. You have an excess pair of chihuahuas running around up here going yip, 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 very negatively charged. It comes up to the water. The water says, I got a dome of negativity up there. I've got my own negativity up here because I've got 2 unbound pairs of electrons. So basically what happens is this, no pun intended. This takes a proton from the water and you make this. So now this has picked up a proton. This now has the deficiency of a proton. So the water's at this point is a little put out. It's negative. It's like, dude, man, traitor, you left me. But it only takes one. It doesn't take both of them. It only has capacity to take one. So we take ammonium, NH4, which has a charge of 1 plus, and we have OH. Now, here's the cool thing about water. In this situation, what is water acting as? Is water acting as the acid, or is water acting as the base? Water is acting as the acid in this situation because it's giving up the proton. So in this situation, water is acting as an acid, and the ammonia is acting as the base. So water is what we call amphoteric. Amphoteric means that water, depending upon the situation, can act as an acid or it can act as a base. That's one of the cool things about water, okay, is that depending upon the situation, you can make it as act as an acid or you can make it act as a base. Now, you have ammonia and you have hydroxide. Now, there's another thing that's going to be important in comparing these two reactions. If I put hydrochloric acid and water in this, I'm going to generate hydronium ions. That's going to make the pH go down. It's going to make the solution acidic. And I'll do this demo eventually. If you take ammonia, which is a gas, and you put it in water, you form ammonium and hydroxide. So this is producing hydroxide, so that actually makes the solution become basic because you're generating hydroxide ion. So in this situation, the solution, you know this is happening because the solution turns basic. That, you know the reaction takes place because you know the solution turns acidic. So in one situation, it turns basic, the other one turns acidic. So, is my NH4 my conjugate acid or my conjugate base? Acid. So here's my conjugate acid. And there's my conjugate base. Because it would have to take in a proton to go back to being the water. Cool with this. So whenever on Bronsted-Lowry, the beauty of this is that you're not limited to just aqueous solutions. When you do this, ammonia actually is a gas. You literally bubble ammonia through water, and it reacts, and you see the solution turn basic. So we have acid-base reactions taking place, but again, this ammonia doesn't look anything near like the traditional Arrhenius definition of being a base, because it doesn't even have hydroxide on it. Okay? There's no oxygen. It has some hydrogens, but it doesn't have that OH. So this is why we need a broader definition of acid-base theory to explain what happens when you see reactions like this. Okay. Now, here's the next thing that we need to look at. So I have equal solutions, concentrations of 0.1 molar hydrochloric acid, and I have 0.1 molar acetic acid. Okay? So they're both the same molarity of acid. Turn the lab quest, well, fires up. So here's what we have. So I have a 0.1 molar solution of hydrochloric acid, and I have a 0.1 molar solution of acetic acid, which is HC2H3O2. All right? This is important. They both have the exact same molarity. Okay? I prepared them both. They're exactly 0.1 molar. Okay? The molarities of these two are exactly the same. Now, what I'm going to do is I'm going to measure the pH of both solutions. So I'm going to do the hydrochloric acid one first. Okay? So I'll measure this one. And I get 1.83. Okay? So this one, forgive me, I'm going to write left-handed. 1.83. Not horrible. Okay? So now I'm going to measure the acetic acid one. So the acetic acid one, even though it's the exact same molarity, that has a pH of get there. Exactly 3. Cool. So the pH of acetic acid is 3.0. Okay? They both have the exact same molarity, 0.1 mole. Let's start with what pH tells you. Okay? Which one of those has the higher concentration of hydronium ions? The hydrochloric acid or the acetic acid? Why? I want a mathematical basis for the answer.
The H is a higher percent of the mass.
Riddle me this. And this is something you need to be able to do. If I just gave you the pH and said, find the hydronium ion concentration. Okay? Well, I just said, here's your pH, 1.85. Find the hydronium ion concentration. What would you do? So if I actually want the hydronium ion concentration, somebody get out a calculator, let's do the math. Okay? So I've got 10 to the negative 1.83. So what do you get when you take 10 to the negative 1.83? 0.015.
Yeah.
That's the concentration of the hydronium ions there, 0.015. Okay, pretty close to 0.01. Okay, I kind of eyeballed it when I was doing the solutions. Actually got pretty closer than I thought it was going to. Now, this one, I'm going to take 10 to the negative 3. So help me, you punch this into your calculator. I'm going to lose my mind. That's 1 times 10 to the minus third. Okay? Because that's what pH means, is 10 to that negative value. Okay? 10 to the negative third is 1 times 10 to the negative third. Okay? Don't use calculator to do that. Like, what's 1 plus 1? Let me punch that in. Oh, 2. Got it. Okay. So, this is 1.5 times 10 to the minus second. That's 1.0 times 10 to the minus third. Okay? So, even though this has a, and here's the dichotomy with pH, even though the pH is bigger, it actually represents a smaller concentration of hydronium ion. Now, let's talk about why this is what it is. So, in both situations, here's going to be the reaction. We're going to take hydrochloric acid, put that in the presence of water. I'm going to generate hydronium ions and chloride ions. Over here, I'm going to have C2H3O2 plus water, getting hydronium ions and the C2H3O2. Yeah. Okay? So the reaction line of this looks identical. Okay? In both situations, you're going to start with an acid, water, hydronium ions, and the anion. The reaction line is the same. The initial conditions on both of these are still the same. 0.1, that's going to be 0.1. Okay? Now, and this is what this boils down to. When you look at hydrochloric acid, it has a much stronger bond to the water molecule than it does to itself. So what that means on that change line, all of this goes away. I don't have any molecular form of that acid. It's gone. Okay? So all of this, that 0, so this becomes 0.1 molar, this becomes 0.1 molar, that becomes 0. This becomes 0.1, that becomes 0.1. Now, let's talk about the ramifications then on Ka. Because this is all one big puzzle that you have to fit together. Okay? So the Ka, any calculation of Ka is your hydronium ion concentration times your anion concentration divided by the concentration of your acid. Okay, and I'm just going to put it in terms of HA and that. So again, what's the only time in chemistry that you use an uppercase K when you're at equilibrium? So if you look at this equilibrium line, and this is the math side of this. At equilibrium, what's the concentration of your hydrochloric acid? 0. Okay? So what do you get when you divide by 0? An undefined value. Okay? Now, let's just say there was a tiny, for the sake of argument, let's say there was a tiny bit of molecular hydrochloric acid still in the solution. Okay? Strangers in the night, hey, let's hook up for a brief moment. So let's say at equilibrium, this is 0.1, that's 0.1, and let's say this is 0.000000001. Okay, tiny bit. So, and I don't want the number on this, I just want you to understand the concept.
Big number.
It's going to be a big number. Why? You're dividing by a very, 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 very small number. Now, here's what I want you to do for those of you that have your books. Okay? If you look at the back of your book, and this is going to be important in terms of today's assignment. If you look at the back of the book, there's a chart of Ka values on. Go. Find it. Okay, on page 1081, there's a chart. This is going to become your best friend for this unit. Page 1081. You're going to post it note. We're going to post it note here so you can find it. Do not dog-ear this corner. You're the first people to use these books. Go gentle on these books. So if you look on page 1081, you have a chart of Ka values. Now, if you give this a cursory look, if you go down that chart of the Ka1 values, what do you notice about all those Ka values? Are they really big or are they small? All Ka values are small numbers. Okay? They're small numbers. Some are 10 to the negative 10. Some 10 to the negative 12. Now, you have one down here, sulfuric acid, and when you go down that chart of Ka1, it just says strong acid. You don't have a Ka value for sulfuric acid. Now, let me explain the difference between Ka1, Ka2, and Ka3. That's referring to how many protons it can lose. So notice that most of these acids are what we call monoprotic. Means they only have one proton that they can give up. But if you look at like arsenic acid, which is H3ASO4, notice that that has 3 Ka values because it has 3 protons that it can give away. Now, this is important. If you look at arsenic acid, and if you look at the Ka1, that's 5.6 times 10 to the minus 30. Ka2 is 10 to the minus 7. Ka3 is 10 to the minus 12. So as you go across on those ones that have more than one Ka value, what do you notice about the Ka values? Are they getting bigger or are they getting smaller? Getting smaller. Now, this is the math side of this. When you look at how you calculate Ka values, okay, this is where you have to understand math. What's the only way you can produce a very small Ka value? What do you know about the numbers up on top?
Small.
They're very small. So if you want a small Ka value, okay, the only way you can have a small Ka value is if you have a small hydronium ion concentration and you have a small anion concentration, but what about the concentration of the original form of the acid? That has to be big. Okay? So mathematically, the only way that you can make a small Ka value is if you have a small hydronium ion concentration, a small anion concentration, and a big molecular form of the acid. So now, conceptualize what this means. So if you look at acetic acid, if you look on down that chart, what's the Ka value for acetic acid? Numeric value.
2.67 times 10.
No, not even close. How about 1.8 times 10 to the negative 5th?
Okay, we were on that.
No, you weren't.
I said,
Okay.
you said synthetic.
So there's the Ka value of acetic acid. So what that means is this. Mathematically, when you multiply the hydronium ion concentration times the anion concentration divided by the concentration of the acid at equilibrium, you're going to generate 1.8 times 10 to the negative 5th. Okay? Now, here's the next comparison. Let's say that you look at a different acid that has a Ka value of 1.8 times 10 to the minus 7. Okay? That Ka value is smaller. So what does that mean if you were to compare these two acids? which one has more hydronium ions in it? The 1.8 times 10 to the negative fifth, or the 1.8 times 10 to the minus seventh? Because that's the only way that you can produce a bigger number. So here's what I want you to see. As you decrease the value of the Ka, the only way that can happen is if you decrease the concentration of the hydronium ions and the anions. So what that means is that when you look at Ka values, the smaller the number is, mathematically that's occurring because you're producing, how you calculate Ka, a smaller value of the hydroniums and the anion. Now we're going to go full circle. Now we're going to go back to Bronsted-Lowry. So you have a weak acid. I'm just going to put it as HA plus hydrogen, or the water yielding H3O plus the anion. If you really want to get simple, just write this as HA turning into H plus and the anions. Pick one, I don't care. Okay, just understand which one. Pick one, I don't care. It doesn't make any difference. But here's what I want you to see. This is going to be acting as the acid. Water is going to be acting as the base. So here's the dichotomy when it comes to weak acids and conjugate bases. I'm going to say this a couple of times so that this soak in. The stronger the acid is, the weaker the conjugate base. So let me give you an example. Stronger the acid, the weaker the conjugate base. So if you look at hydrochloric acid is an exceptionally strong acid. It's one of the 7 strong acids. And the reason that it is a strong acid is because basically once you separate it, it has no desire to go back and reform the molecular form of the acid. It is much more stable being separated. So listen to me. If you have a strong acid, you have a weak conjugate base. So what that means is that this chloride basically has no desire or ability to hook back up with that proton and reform the acid. Okay? You went to prom literally as just friends. Okay? You got set up for this. And friends said, oh, you're going to make it. So you went as friends. But as soon as you got to the dance, man, like you are separated. So you have a very, very, very weak bond with that person. Okay? You are not going to reconnect at prom. Okay? You get in the door, boom, separated. Okay? So if you're a strong acid, what allows you to be a strong acid is the fact that you have an exceptionally weak conjugate base. Okay? Now, in contrast to that, if it is classified as a weak acid, weak acids, in contrast to that, have strong conjugate bases. So if you take something like acetic acid and you separate it out, it goes, whoa, 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 this is bad, okay? I'm alone, I'm not digging this. So what it does is that it goes back up to the water and goes, knocks on the door and says, hey, excuse me, I want my date back. That was a mistake. I was upset. I said things I shouldn't have. I want my date back. Okay? And the proton says, hey, my bad. I'll always forgive and let's go back together. So they might momentarily separate, but they're going to be much more stable as the molecular form. So if you have 100 of these molecules, the molecular form, out of any given point, typically maybe 3% are ionized. So out of those 100,